shall be less equal to 180 microwatt. So in the previous design example, we considered only two performance metrics, that is gain and power dissipation. Today we are adding another performance matrix, that is called gain bandwidth or unity gain frequency. Frequency of greater equal to say 100 megahertz, and whenever this unity gain frequency is specified, it will be for a given capacitive load. So for CL is equal to 1 picofarad. If we do not specify the load capacitance, then this unity gain frequency specification will not make sense, right? So now we have been given with this specification of common source amplifier, and as I have already told you that we have extracted the technology parameters. So we will use the hand calculations first, and then we will go ahead and verify our hand design through simulation. So let's first see the topology, and let us consider this topology. There are many more topologies for common source amplifier with diode load. So let me consider with this topology. So VDD is 1.8 volt. And where shall I connect? So here you see this M1 is the driver, right? We will be taking output from here, and this load capacitance is connected here, 1 picofarad. This is 1 picofarad. So where shall I connect the gate of M2? In place of M2, we had resistance in the common source amplifier with resistive load. So there the load was resistance. Here we want to use diode connected MOSFET as a load. So where this gate shall be connected to realize a diode connected MOSFET? Anybody any idea? How do we connect MOSFET to realize a diode? Where shall I connect the gate of MOSFET? To its drain, right? So yes, that's correct. We shall connect it to the drain. Okay, right. So this forms the diode connected MOSFET. Now if we have to let's see the expression, let's derive the expression for gain. So let's say this is resistance looking up, resistance looking down, and therefore R out will be R up parallel R down. Now R up, so you are looking into the source of the transistor, diode connected transistor. So what is the resistance seen looking into the source of diode connected transistor? Do you remember?
1 by GM2.
Yes. So this comes out to be 1 by GM2 parallel. R down is nothing but the resistance looking into drain of MOSFET M1, and you see RO1 here, and which is actually approximated as 1 upon GM2, because 1 upon GM2 is, so this is under the assumption that 1 upon GM2 is very less than RO2. We will verify it, right? So once we have got the expression for R out, we can write gain mod of AV is equal to GM1 into R out. R out is GM2, so this comes out to be, and if we write GM1 like this, 2 mu n C ox W upon L1 ID1 upon square root of 2 mu n Cox W upon L2 ID2. So, but ID1 and ID2 will be equal. Do you agree?
Yes, sir.
So this comes out to be this. We get an expression of a square root of W upon L1 upon W upon L2. Do you agree?
Yes, sir.
So what we see over here, that the gain of this diode connected, gain of this common source amplifier with diode connected load is actually the ratio of the width of the two transistors, and this L, if we take the length of both the transistors to be same, then it will simply be a square root of W1 upon W2, right? Now we have been said that the gain is greater equal to 5 in the specification. So we can write that square root of W upon L1 upon W upon L2 shall be greater equal to 5, and therefore we can write W upon L1 shall be greater equal to 25 times W upon L2. Am I right?
Yes, sir.
So we have got this relation between the width of the transistors from the gain specification, right? Another specification is the power dissipation specification, and we have earlier worked uh, using power dissipation specification, using power dissipation specification. We have got that ID shall be less equal to 100 microampere. We did that calculation in the previous example. There also the restriction on the power dissipation was 180 microwatt. Here also the restriction on power dissipation is 180 microwatt. So we got this value na, in the earlier example. Do you remember?
Yes, sir.
So now we have, sorry, let's say this is 1, this is 2, and then gain bandwidth. So do you all understand gain bandwidth? See, when we have, so let me first derive the expression for gain bandwidth. So this is AV in dB. So this is called gain bandwidth or unity gain frequency. Gain bandwidth product or unity gain frequency or GBW, right? So gain here is given by GM1 upon GM2, and this is first pole frequency, so which is also referred to as minus 3 dB frequency, and it is given by 1 upon 2 pi CL R out. R out is how much? 1 upon GM2.
Yes, sir.
So 1 upon GM2. So this becomes GM2 upon 2 pi CL. So in the given problem, the specification regarding gain bandwidth is that it shall be greater equal to 100 megahertz for a load capacitance of 1 picofarads. So let's try to find. So using the gain bandwidth specification. Okay, so how, let me first derive the expression of gain bandwidth now. So gain bandwidth, see, this gain bandwidth product is given by this gain multiplied by this bandwidth, right? So if you multiply that, so gain bandwidth is given by GM1 upon GM2 into GM2 upon 2 pi CL, and therefore you get GM1 upon 2 pi CL. You understand?
Yes, sir.
Okay. So now from the given specification of gain bandwidth, we can write, now from the given specification of gain bandwidth, from the given specification of gain bandwidth, we can write that Gm1 upon 2 pi CL shall be greater equal to 100 megahertz. And from here, we can get Gm1 shall be greater equal to, see, 100 into 10 to the power 6 into 2 pi into CL is 10 to the minus 12. So can you work it out and tell me the value of the right hand side expression? So Gm1 shall be greater equal to 2 pi into 10 to the power minus 8. 2 into 3.14.14. So 6.84. So it comes out to be 6.28 into 10 to the power minus 4. Do you agree?
Yes,
Siemens
sir.
or ohm inverse. This is the expression, this is the requirement for GM. Okay. So from here, we can use this, we can write GM1 as 2ID upon VOV, and this shall be greater equal to 6.28 into 10 to the power minus 4. We can, from here, we can use, say, 2ID, or I shall use ID shall be greater equal to 3.14 into 10 to the power minus 4 into. Now we have option to choose the value of VOV, and we know the typical value of VOV is in the range of 100 to 200 or 250 millivolt. So let's take 150 millivolts, so 0.15. So this implies that ID shall be greater equal to, so this comes out to be how much? 3.14 into 0.15, so 0.47. This comes out to be 0.47 into 10 to the power minus 4, or say 47 microampere. Agreed?
Yes, sir.
So from the power dissipation requirement, the requirement is that ID shall be less than 100 microampere. And from here, and you shall remember that here we are taking VOV is equal to 150 millivolt. This we will use to size the transistor. Okay. So from here, you see what we got. So from this exercise, we got that, or I shall write it like this, VOV1, that is M1, this is equal to 0.15 volt, and ID1, this is equal to how much? Let's take it 50 microampere, for example. We can take it 50 microampere, greater than 47 microampere and less than 100 microampere. So we can choose any value in between this range. So if I have taken it to be 50 microampere, so now we have the overdrive voltage of M1 transistor and the current of M1 transistor. So we can write ID1 is equal to half mu Cox W upon L VOV1 square into 1 plus lambda VDS. So we can write half into, what was the value of mu Cox? 150 into 10 to the power minus 6 into W upon L. This we have to actually find. W upon L1 into, so 0.15 square into 1 plus lambda is 0.16 into, again, VDS of M1. So suppose we want V out to be 1 volt. So VDS will be 1 volt. You understand? I am designing this amplifier for output, DC output, this DC output, the voltage here, 1 volt. You understand? Say something, yes or no.
Yes, sir.
So this comes out to be 1. And here on the left hand side, you have 50 into 10 to the power minus 6. So can you solve and tell me the value of W upon L1? What is the value of W upon L1? Do the calculation. I'm also doing the calculation. You also do it and tell me the value. So this will be something like 100
25.54.
into 10 to the power minus 6 upon 150 into 10 to the power minus 6 into 0.0225 into 1.16. Is it so?
25.54.
So this comes out to be 25.54.
54.
Okay. So, okay. Yes. And you remember this requirement, W upon L1 shall be greater or equal to 25 times of W upon L2. Right. So this implies, so from here we got, say, length of transistor 1 is equal to 0.36 micrometer and width of first transistor will be how much? So 0.36 into 25.54 comes out to be 9.19. So I will actually approximate it to be 9.2 micrometer. So we have got, now from here, from the earlier relation, we will have W upon L 2, we can take 1 micrometer. If we take W upon, this is 25.54, if we take W upon L2 to be 1 micrometer, so this relation will be satisfied. If W upon L2 is 1 micrometer, sorry, is 1, not 1 micrometer, W upon, this will be unitless quantity, no? If we take W upon L2 to be 1, so W upon L1 is greater or equal to 25 times W upon L2. Can we do that? You
Yes,
see
sir.
this relation? Do you see that? Now let us verify also. So we are getting this thing we are getting from the gain expression, but we also have ID expression. So we can also write ID2 is equal to half mu C ox W upon L2 and VOV2 whole square into 1 plus lambda VDS2. ये भी तो satisfy होना चाहिए ना, ये requirement भी.
Yes, sir.
So let's do that. Let's see if we get this requirement satisfied or not. So we will again write 50 into 10 to the power minus 6 is equal to half into 150 into 10 to the power minus 6 into W upon L2 into what will be VOV2? Can you tell me? What will be VOV2? We are assuming that the voltage here is 1 volt, DC volt. So VGS will be how much? VGS for this transistor will be how much? VGS2. बताएं भाई.
0.8.
0.8 volt, yes. Gate is at 1.8 volt and source is at 1 volt. So VGS will be 0.8 volt, right? So let's go there. So we can write 0.8 minus threshold voltage हम लोग इसका 0.45 assume कर रहे हैं. This will be a square and 1 plus lambda is 0.16 into VDS will be now how much? 0.8. So can you do the calculation and find W upon L2 from here? So it shall be again 100 into 10 to the power minus 6 upon 150 into 10 to the minus 6 into this will be 0.35 square. 0.35 squared. So 0.1225. 0.1225 and this will be 1 plus 0.16 into 0.8, 1.128. What value do we get?
$4.82.
Just a minute. Yes, we get W upon L2 4.82, right? So if we now we have we got W upon L2 to be 4.82 and W upon L1 to be 25.54. So obviously W upon L1 is not 25. So this requirement, you see this requirement we are not meeting. So what shall we do to meet this requirement? So what we shall do, let's go ahead and let's meet that requirement through simulation. Okay, so L2 is equal to 0.36 micrometer and W2 is equal to, so what will be W2? into 0.36. So comes out to be 1.73 micrometer. So we have got all the values. L1 is equal to 0.36 micrometer and W1 is equal to how much? W1 is 9.2 micrometer and VOV1 is equal to 0.15 volt. From here we can write VGS1 minus VTHN is equal to 0.15 volt, and from here we can write VGS1 is equal to 0.15 plus 0.45. This comes out to be 0.6 volt. Okay. Now what we can actually do if we want to have W upon L1 to be higher, can you suggest? Can you suggest this W upon L1 is right now not 25 times of W upon L2, and therefore what is going to happen, we are not likely to get the desired gain. So okay, let's go simulate it and let me demonstrate, and then we will come back to this and see how we can do iteration to achieve the desired gain. So let's go ahead and create the schematic first. So I will actually open the schematic, earlier schematic, and edit it. So I will save it as, common source amplifier with diode load dot ASC, and then I will actually delete these things because I need N MOSFET. I need N MOSFET all. So okay, so I will use it to create the new schematic. So NMOS 4. Okay, let's take NMOS 4, put it here like this, and then we need one more NMOS. So I will create a space here. I can copy this NMOS, place it right here like this, and then I can do the connections. Place this. Let me connect it with the so I will also ground the body of this N MOSFET, and the gate of this N MOSFET is to be connected to the drain, so it is connected to drain. Then this is to be connected here. Yes.
सर आपने
Yes.
मतलब ग्राउंड किया है, बॉडी से कनेक्ट नहीं किया, मतलब बॉडी को से सोर्स से कनेक्ट नहीं किया.
हाँ, I told you that the body of N MOSFET is connected to the most negative voltage, but this is going to pose a challenge. अभी जो मैंने कनेक्शन किया है उसकी वजह से बॉडी बायस इफेक्ट आएगा पिक्चर में, and if you want to keep it simple, actually you can do it, which actually is not the very correct way, right? Like this. But if you remember yesterday, I told you that the body of N MOSFET is connected to the most negative voltage available in the circuit, and body of P MOSFET is connected to the most positive voltage in the circuit. Okay, let's go ahead with this connection, which is not altogether wrong, but it actually poses challenge in doing the layout. But the advantage of this connection is that the threshold voltage does not vary with the voltage swing at the output, because VSB is 0. So body bias effect will not be there. Okay. So let's size the transistors. So first of all, let me bias this we found to be 0.6, this bias voltage. Then the length of M1, length and width of M1 we have found to be 9.2 micrometer. So let us write 0.36 micron, 9.2 micron, 9.2 micron, sorry, 2 micron. Similarly, for M2, it is 1.73 micron. So width is 1.73 micron and length is 0.36 micron. So I think we have done all the connections and we are ready to do the DC simulation. So let's first do the DC analysis. DC analysis by sweeping V2 from 0 to 1.8 volt in the steps of 10 millivolt. And let's see V out. Okay, let's also see the width of these transistors on the schematic. That actually helps us. So I will place it here. This I will place here. Okay. So we have done the simulation. Let's plot the V out. So this is V out versus V in. We can see some more. Let me add some more plot pins. So right. Okay, so that we can see the current and everything. So I am also plotting current. So this is IDM1. Okay, and I will plot V out here, and this I will plot as gain, so that we can see all the three plots simultaneously. Okay, so you can see that the gain that we are achieving is the maximum gain that we can get is 3. We are not getting a gain of 5. Do you see that? This is the gain plot. This is the V out level, right? And this is ID. So what we see that we are not getting gain. Desired gain, we are getting a gain of 2.9 or something like that, which is again for VGS of 729 millivolt, and currently the bias with the bias voltage of 0.6 we are getting a gain of 2 only. Do you understand that?
Yes, sir.
So how shall we actually increase the gain? The question is that we want to increase the gain, and from having all the three plots simultaneously, what we can do actually, we can observe the gain. You see, we can, from this plot we can observe the gain. From this plot we can observe the voltage level at the output, and from this plot we can observe the current. So having all the three plots simultaneously actually helps us in meeting all the requirements. Means we can simultaneously see what is the output voltage level and what is the current, so that the power dissipation is not violated, right? So what do you suggest? What shall we do? The gain, we are not meeting the gain requirement, and the reason is that the width of
सर अगर हम इसमें VOV इंक्रीज कर दें सर,
that looks from here we see that, okay, you are saying that, okay, we increase VOV, still we will be get a maximum gain of 3, but you shall also see that the current is going beyond 100 microampere. So certainly we cannot do that. Do you notice that?
Yes, sir.
नहीं कर सकते ना हम, जैसे अगर मैक्सिमम यहाँ पे अगर 3, 5 तो वैसे भी नहीं मिल रहा, 3 मिल रहा है मैक्सिमम गेन, लेकिन उस मैक्सिमम गेन को अचीव करने के लिए अगर हम VOV बढ़ा देते हैं, 0.7 कर देते हैं, 0.75 कर देते हैं, तो क्या हो जा रहा है, ये करंट की रीडिंग भी तो देखिए, the current goes beyond 100 microampere, so it is actually violating the power dissipation requirement. So what shall we do?
Increase output resistance.
क्या कह रहे हैं आप?
Output resistance को increase करने से.
हाँ, but how?
सर वैसे ये तो VDS वर्सेस कर्व है, VDS, अच्छा ओके सॉरी,
तो गेन ही तो प्लॉट किया ना, रेड प्लॉट जो है that is gain plot, and you can see that you are getting a maximum gain of -3 only. और अभी जो करंट बायस वोल्टेज है 0.6 वोल्ट के लिए तो गेन और भी कम आ रहा है, 2 आ रहा है. So what can we do?
Sir, DC का ट्रांसकंडक्टेंस डिक्रीज करोगे.
ट्रांसकंडक्टेंस क्या कह रहे हैं आप, फिर से बोलिए.
डिक्रीज कर दे
डिक्रीज कर देंगे ट्रांसकंडक्टेंस को,
M2 का, M2 के
Yes, sir.
ट्रांसकंडक्टेंस को डिक्रीज करना है ना.
Yes, sir.
You are right. We can decrease the transconductance of M2. So अभी जो हम लोगों ने M2 50 microampere current, what we are doing actually, we are passing whole 50 microampere current through this transistor, right? Now to decrease the transconductance of M2 while having same overdrive voltage, we shall decrease the current flowing in this transistor M2. Agreed?
Yes,
Yes,
sir.
sir.
But if we decrease current in M2, the current in M1 will also decrease.
यस सर,
So we cannot directly decrease the width of M2 to decrease the current through M2, because when the current through M2 decreases by decreasing the width, the current through M1 will also decrease and therefore there will not be any change. समझ रहे हैं आप? अगर हम इस दोनों के विड्थ को हाफ कर दें अभी, तो भी गेन पे कोई फर्क नहीं पड़ेगा, बिकॉज द करंट विल रिमेन सेम.
यस सर,
ठीक है. So what actually we can do, let's see that interesting thing. So I will do what? I will add a current source which later we will see can be designed using a transistor. So now what I will do, now suppose total 50 microampere current flow कर रहा था M2 से, 50 microampere ही करंट फ्लो कर रहा था ना, हमने 50 microampere करंट लिया था ना.
Yes, sir.
Now what we can do, if we assign 25 microampere current, or you can assign even larger, say, okay, let's say you assign 40 microampere current through this current source, then the current through this transistor will be only 10 microampere. So we shall actually redo this calculation. ये तो हमने 50 माइक्रोएम्पियर के लिए ये कैलकुलेट किया ना, W/L2. Getting the point or not?
यस सर।
लेकिन अब तो हम क्या चाह रहे हैं, हम चाह रहे हैं कि इस M2 से सिर्फ 10 माइक्रो एम्पियर करंट फ्लो हो, तो हमें फिर से तो लेंथ और विड्थ फाइंड आउट करना चाहिए ना इसका,
यस सर।
राइट? सो अगर हम फिर से लेंथ और विड्थ फाइंड आउट करें तो हमने बेसिकली करंट को क्या कर दिया है, 10 कर दिया है ना। सो क्या हो जाएगा यहाँ पे बताइए, इसको कैसे एडिट कर दें। Now this is 10 microampere only, so this will become 20 microampere, or you can say that this ratio will become 1/5, 1/5 हो जाएगा ये। देखिए ना, न्यूमरेटर जो है वो 1/5 हो गया ना,
यस सर।
बाकी चीजें तो सेम है ना, ओवरड्राइव वोल्टेज एवरीथिंग इज सेम। So this will also become 1/5, means W upon L2 will become 0.96. Do you understand?
यस सर।
Is anybody having any query? Anybody having any query regarding this? So from here, now see what we need to do. If you take length is equal to 0.36 micron, then W has to be less than 0.36 micron.
Yes, sir.
Or you can say that, okay, W is nearly equal to 0.36 micron. So if we take length and width to be 0.36 micron for this transistor, let us see the behavior. Let's take the width also to be 0.36 micron. And let's do this simulation. So do you see the result?
यस सर।
Let me restrict this to 1 volt only so that you can see it more clearly. Okay. And this, let's take it to be T. Okay. So you can see that we are able to achieve a very high gain.
यूजिंग डीसीटी। सर आज तक यही पढ़ाया गया था कि ये अचीव नहीं कर सकते।
ये नहीं कर, हाँ, so if you can use सिर्फ only a diode connected load, that's why you are learning a new thing, how to increase the gain of a diode connect, a common source amplifier with diode connected load. So if you can add a current source in the parallel like this, and you shall go and see that section in the Razavi's book. I think you have missed that section in the Razavi's book where the common source amplifier with diode load has been discussed. An example problem is there where you will see that a diode connected load is there and in the parallel a current source has been used. So this is actually a technique, a trick using which you can increase the gain of a common source amplifier with diode load.
सर आपने ट्रेड का मतलब इससे कुछ कम भी हो रहा है इसमें?
क्या चीज कह रहे हैं? मैं कह रहा हूँ ये ट्रिक है, इस तरह से हम ये कॉमन सोर्स एम्पलीफायर विद डायोड लोड का गेन हम बढ़ा लेते हैं. I'm saying it's a trick, it's a technique to increase the gain of a diode connected common source amplifier with diode connected load. So I think many of you are having some doubt So nobody is saying anything. क्या? Shall we go ahead and do the transient simulation?
Yes, sir.
And obviously, there will be some non-ideality when you implement this, say, of course, this current source has to be implemented using a transistor now.
That's everything is right.
You can also see a different situation where you, okay, say only 20 microampere current is, or only 30 microampere current is allotted to this, and then the current through this is actually doubled, so you can double the width, and you can again do the simulation. Right? So you can do many things, but ultimately when you will implement this current source using a PMOS transistor, actually you will have to replace this PMOS transistor and then the biasing circuit for that. So circuit of course becomes a little complex, but this is the concept, how you can increase the gain of a common source amplifier with diode connected load by making current through P MOSFET this load lesser and diverting the current through this. If you want to see the theoretical concept, okay, let me show you. So what we are doing here, we are having this diode connected transistor. Let me show you it through analytically. And then we have connected a current source here. And this is V out, right? So this is VDD. So suppose this is ID, and suppose this is 0.75 ID, and the current through then here will be 0.25 ID. Do you understand?
Yes, sir.
So now when you write the gain expression, so gain expression now when you write, so again it will be, this is M1, this is M2. So you will write GM1 upon GM2. This is how you will write it. Okay.
Yes, sir.
Now GM1 again you will write as 2 mu C ox W upon L ID2 upon square root of 2 mu C ox W upon L 1 ID1. यहाँ से, no, I think I did it wrong. न्यूमरेटर में 1 होगा ना, ये 1 होगा ना, डिनोमिनेटर में 2 होगा. So this will be W1 ID1 W2 ID2. तो अब जो गेन का एक्सप्रेशन हो जाएगा वो क्या हो जाएगा, स्क्वायर रूट ऑफ W अपॉन L1 ID1 upon W upon L2 ID2. Getting the point or not? In the previous derivation, ID1 and ID2 was equal. You see here. ID1 and ID2 was equal, no? And that is why we got the gain expression, that is square root of W upon L1 upon W upon L2 only. But if we use this technique, another branch to share the total current. So this ratio you can adjust 75% and 25% of ID or whatever. But now you can see that in the gain expression, 25%, right? So what it means for the given case, it will become 2 times of a square root of W upon L 1 upon W upon L 2. ये हो जाएगा ना point 1 upon 0.25, that comes out to be 4, and square root of 4, so 2 comes out.
Yes, sir.
Do you understand this?
Yes, sir.
So this is actually a trick to increase the gain of a common source amplifier with diode connected load, while keeping the benefits of diode connected load, like the linearity and uh, resistant to process variation. Because you see now here it is the ratio of the width of the transistors, aspect ratio of the transistors. So it will not have the demerits of the common source amplifier with resistive load, where the mismatches can result into significant variation in gain. Here the mismatches will not have significant variation in gain because it's a ratio of the aspect ratio of two transistors. Is that clear? So as one of you pointed out, obviously you are surprised to achieve such a high gain using a common source amplifier with diode connected load, right? But here we are getting a gain which is extraordinarily high. Usually even this technique we will employ to get a gain of say 10 or 15, not as high as 60 that we are seeing over here. So we could have been a little, say, actually we could have kept it like this. Only 10 microampere current goes through this, and then if so what shall be the width? So if it becomes uh, 10 microampere, so 40, it becomes 40, uh, so it becomes 80, for example. Let me do it. So suppose we are doing this only 10 microampere current through this current source, and remaining 40 remaining 40 microampere through this transistor M2. Then also we can have this 40 into 10 to the power minus 6 is equal to half into 150 into 10 to the minus 6 into W upon L2 into what was this fraction? This came out to be 0.1225 into 0.1225 into 1 point something we already calculated, 1.128. 1.128. And from here, so can anybody tell me from here this 80 into 10 to the power minus 6 upon 150 into 10 to the minus 6 into 0.1225 into 1.128. So can anybody tell me the value? 150 into 0.1225 into 1.128 inverse into 80, that comes out to be 3.85. So you can take length is equal to 0.36, width is equal to into 0.36, 1.39. So if we take this to be 1.39, then also you can see no, but something is going wrong. Did I do some calculation mistake or what? Because it is not working now. If I revert it back, this is fine. Uh, so with a bias voltage of 0.6, we are getting a gain of say 5.57. And from here you can also see the output voltage is also, so you can see the output voltage to be around, yes, it is 1.07, and you can also see the current which is around 46 micro ampere. So it needs a, so now if we want to observe the gain bandwidth product, so we need to do the AC simulation. So
करंट तो 47 से ज्यादा होना चाहिए था ना
50, we designed it for 50, right? We designed it for 50. It comes out to be 46 microampere. Okay. So we will have to tune the design to meet these, but let us go ahead and do the AC simulation to measure the gain bandwidth product. Of course, we will fall short of the desired gain bandwidth product because of the smaller current, but let us go ahead and do the simulation. So let's do the simulation. So here we won't need I1, we don't need this. We need only the V out. So this, we can just get rid of this. Okay. So we are getting a gain of say 14 dB, which I think around 5 point something, 20 log 5. Yes. So this 14.5 dB is again greater than 5, and okay, we are meeting the gain bandwidth requirement even. So it comes out to be 113 megahertz. The gain bandwidth requirement wanted us to have the current greater equal to 47 microampere. I think I did some calculation. Yes, here. And right now, the current that we are having, is 46.1 microampere. But you shall also be aware that this 47 microampere current we got with an overdrive voltage of 0.15 volt, and we are assuming that the threshold voltage is 0.45, but maybe the threshold voltage is little larger than 0.45, and that's why the overdrive voltage is little smaller, and therefore we satisfy this requirement even for a current of 46 microampere instead of 47 microampere. Is it possible or not? This is the requirement that we want to satisfy, and we got that the current shall be 47 microampere for an overdrive voltage of 150 millivolt, right? And that overdrive of 150 millivolt is assuming the threshold voltage to be 0.45. But what could be happening that the threshold voltage is little greater than 0.45, and therefore the overdrive voltage is little smaller. Actually, we can go and see the threshold voltage of transistor M1 if we go to spice error log. Just a minute. We shall be able to see view where do we get the output file?
सर वो .op से आता है.
We have not, yes, we shall include .op command first. Yes, you are right. Thank you. Control M .op. Yes. Let's go and see the threshold voltage of, yes, M1. VTH of M1, you see, it is 466 millivolt now. And in our hand calculation, we are taking it to be 450 millivolt. So threshold voltage is a little higher. It means that the overdrive voltage of this transistor is a little lower, and therefore 46 माइक्रोएम्पियर करंट के लिए भी आपका ये जो रेशियो है, it satisfies this requirement. Do you understand?
Yes sir.
So this is how we design a common source amplifier with diode connected load, and the technique using which you can actually increase the gain of common source amplifier with diode connected load. So you shall go and see this section in the Razavi's book, and you will be able to appreciate this concept. So that's it for today. Is there any query? Anybody having any query?
सर जब ये हम
हाँ बोले.
जब हम सर ये करंट सोर्स लोड को हम रिलाइज करेंगे पीमॉस से, तो उसका वो नहीं है,
Output
R0
resistance.
नहीं है. यस सर.
Yes, very good question. Very good question. So what will happen? What will happen in this case? जो R up होगा, just a minute. Yes, R up, यही तो होगा ना. तो R up जो हो जाएगा अब, वो हो जाएगा 1/GM2 parallel RO of, suppose we replace this by a PMOS transistor like this, a current source. यही तो होगा.
Yes
So
sir.
now R up will be what? 1/GM2, and let's say this is M3. RO3, यही होगा ना?
Yes sir.
Now again,
again कर सकते हैं और ज्यादा बढ़ाने के लिए, वो तो सेम ही रहेगा.
yes, again you can assume, approximate it to be 1/GM2. Is that clear?
Okay sir.
Anybody else?
यस सर. सर मैं ये पूछ रहा था, जो आपने लास्ट असाइनमेंट दिया है उसमें आपने अप्रोक्सीमेटली 5 का गेन कहा है,
हाँ,
लेकिन
हाँ.
अब अगर एग्जैक्ट वही पैरामीटर्स, क्योंकि आपने उसमें ग्रेटर देन इक्वल्स टू ऐसा नहीं दिया हुआ है, तो उसको एग्जैक्टली अचीव करने के लिए तो फिर तो उसमें 360 मिलीवोल्ट्स वीओवी
नहीं,
चाहिए
मैंने अप्रोक्सीमेटली 5 कहा ना, तो इसका मतलब क्या है? 4.8, 4.9, 5.5, 6 ग्रेटर देन, मतलब ग्रेटर इक्वल टू 5 यू कैन से.
ओके सर, थैंक यू.
हाँ, हाँ. अच्छा, ये क्यों लेते हैं आप? जीएम वर्सेस वीओवी प्लॉट कर सकते हैं. चलिए मैं आपको दिखाता हूं अभी क्यों लेते हैं. ओके, दैट इज वेरी गुड क्वेश्चन. लेट मी शो यू. Let me open this threshold voltage extraction and let me plot this, and let us do the analysis of एक सिंगल प्लॉट का हम करते हैं. k is equal to 2. ठीक है, ये आईडी वीजीएस प्लॉट है. ओके, डू एग्री? सो दिस इज आईडी वीजीएस प्लॉट. अब इसका अगर हम जीएम प्लॉट करना चाहते हैं तो हम क्या करेंगे? इसको करंट को डिफरेंशिएट कर देंगे. करंट को डिफरेंशिएट कर देंगे तो ये हो गया, ये जीएम प्लॉट आ गया. फाइन. अब जीएम प्लॉट आने के बाद एक और प्लॉट करते हैं. रुकिए, लेट मी ऐड just a minute, then we will be able to understand. That is actually very good question. इसको क्या करूं मैं? कैंसिल. रुक जाइए, just a minute. यहां से मैं बस एक रखना चाहता हूं, यहां भी वही प्लॉट कर लेता हूं पहले मैं। एक्चुअली आई विल शो यू। फाइन। उसके बाद ओके, राइट, इसको मैं डिफरेंशिएट करता हूं एक बार, तो ये हो जाएगा ट्रांसकंडक्टेंस वर्सेस VGS, और इसको मैं प्लॉट करता हूं GM ओवर ID। तो इसको मैं पहले डिफरेंशिएट करता हूं। ओके, सो ये नीचे वाला प्लॉट जो है दिस इज GM ओवर ID, एंड ये ऊपर वाला प्लॉट जो है वो GM है। और वर्सेस ओवर ड्राइव अगर करना है तो ये VGS में से थ्रेशोल्ड वोल्टेज में माइनस कर देता हूं। अब देखिए, ये नीचे वाला प्लॉट जो है वो GM ओवर ID है, और ये ऊपर वाला प्लॉट जो है वो GM है। अब आप अगर देखें, आप GM ओवर ID का क्या सिग्निफिकेंस है, चलिए GM ओवर ID का सिग्निफिकेंस पहले मैं बताता हूं। अगर आप ये एम्पलीफायर डिजाइन कर रहे हैं, कॉमन सोर्स एम्पलीफायर विथ करंट सोर्स लोड, यू नो दैट ना, तो इसका गेन जो होता है AV इज इक्वल टू क्या होता है, GM1 इंटू RO1 पैरेलल RO2 होता है। इसको लिख सकते हैं GM1 इंटू 1/λ1 ID प्लस λ2 ID लिख सकते हैं, और इसको लिख सकते हैं GM1 ओवर ID इंटू 1/λ1 प्लस λ2, ऐसे लिख सकते हैं।
यस सर।
अब यहां पर देखिए कि गेन को इंक्रीज करने के लिए दिस कंपोनेंट शैल बी हाई, और ये तो आपने लेंथ फिक्स कर दिया तो ये फिक्स हो गया।
यस सर।
So this GM over ID shall be high. This is also referred to as transconductance generation efficiency. Transconductance generation efficiency. अब चलते हैं वापस हम इस प्लॉट पे। तो यहां से ये तो समझ में आ गया ना कि GM ID shall be high.
यस सर।
अब इस यहां पे आ जाइए आप, तो आप देखिए ये ओवरड्राइव वोल्टेज है। अब तो ये GM ओवर ID की वैल्यू अगर आप लें तो यहां देखिए ये 20 से लेकर के या 200 मिली वोल्ट। देखिए ये 12 से 20 या 10 से 20 के बीच में यहाँ पे चेंज हो रहा है, और ओवरड्राइव वोल्टेज इंक्रीज हो रहा है तो क्या हो रहा है, GMID डिक्रीज हो रहा है, GM ओवर ID। डू यू सी दैट?
यस सर।
तो यहां से आप ये देख सकते हैं कि जो ओवरड्राइव वोल्टेज अगर आप इंक्रीज करें तो GM ओवर ID जो है वो डिक्रीज हो रहा है, और GM ओवर ID हम चाहते हैं क्या, इट शैल बी हाई। तो जो एक्सेप्टेबल, आप कह सकते हैं कि इस रीजन में तो GM ओवर ID और भी ज्यादा है, लेकिन ये जो रीजन है ना ये सब थ्रेशोल्ड रीजन में चला गया है, ये मॉडरेट इन्वर्जन रीजन में नहीं है। तो वो उस रीजन का जो डिजाइन होता है वो अलग होता है व्हेन VGS इज लेस देन थ्रेशोल्ड वोल्टेज। ठीक है, तो आप देखें कि ये 100 मिली वोल्ट से मतलब ये 10 से 20 इज द रेंज ऑफ GMID दैट वी टारगेट फॉर। सो GM ओवर ID का जो हम लोग जो भी डिजाइन करेंगे वो GM ओवर ID का जो रेंज लेंगे वो 10 से 20 के बीच में ऐसे रहेगा, और 10 से 20 का रेंज जो GM ओवर ID का मिलेगा वो आपको ओवरड्राइव वोल्टेज इस रेंज के 100 से 200 मिली वोल्ट के रेंज में मिलेगा, या 250 मिली वोल्ट ले लीजिए, ऐसे ले लीजिए। इज दैट क्लियर नाउ?
यस सर।
any other query? Okay, so if there is no query, I will close it. And I have shared the tutorial, common source amplifier design tutorial with you. So you shall use that tutorial to design, say, common source amplifier with diode load. But that is simulation based approach. What we are doing in this internship, that we extracted the technology parameters, we are doing hand calculation, and using that hand calculation we are just sizing the transistors, और it is actually meeting results pretty good ना, जो भी हम लोग सिमुलेशन कर रहे हैं हैंड कैलकुलेशन के बाद, तो हैंड कैलकुलेशन और सिमुलेशन रिजल्ट्स काफी क्लोज है. सो इट एक्चुअली reduces द सिमुलेशन इटरेशंस, कितनी बार आपको ट्वीक करना पड़ रहा है सिमुलेशन में. So that's why the hand calculation is important. Okay, so if there is no further query, I will stop today's session. Thank you.